Can you hear me? Okay, that means no. Okay, good. Can you hear me now? Okay, good. Thank you, and sorry for the late appearance. Last time we had this course, like with this session on Markov decision process as part of the model-based reinforcement learning, and I told you now I would send the dynamic programming part, which is already pre-recorded before this class. I didn't, so I will send that one along with the MDP video right after this class. Anyway, just I will start this class by kind of revising or giving you some insight about the dynamic programming aspects of reinforcement learning. In the previous class, we have been discussing about Markov decision process, and we said Markov decision process is a kind of a decision process that helps us to build a model of some environment. That was the idea. So we discussed about Markov property, and given a Markov property, a property where just some agent having its current observation or its state will have the capability to come up with reward or whatever, like an action from some policy, as if it consumed or as if it had an exposure for the total history of the agent's previous interaction. Okay, so that was the idea. We tried to see different examples of Markov property, and right after that, we in the introductory part of the previous session, I tried to discuss about what dynamic programming is. Then, from this perspective, given some Markov decision process and the environment, an MDP environment, which is a model of the environment, then algorithms under dynamic programming helps us to come up with optimal solutions, or for the agent, it will provide optimal solutions. So the two prominent algorithms under dynamic programming are value iteration and policy iteration. Okay, so we have been discussing about value of state, policy, value of state and action value in the previous consecutive classes. So when you come to dynamic programming, as part of the dynamic programming related techniques, value iteration is more to the Bellman expectation equation. So the value iteration consumes the Bellman expectation equation. We discussed about Bellman expectation equation last time. And policy iteration consumes the Bellman optimality equation. So the whole topics under the value iteration and policy iteration, which is under dynamic programming, discusses about how to implement or how to come up with a solution space given the Bellman expectation equation and the Bellman optimality equation. I have this pre-recorded video of that. I will provide you that one along with the MDP pre-recorded video that we had together last week or last time, I guess. So today I'll be discussing about model-free prediction. This is you can consider this one as a major branch when you walk across the different topics of reinforcement learning, because so far we have been discussing about reinforcement learning where the model is given, right? So for instance, we consumed MDP as a model or as an abstraction generator of the environment in the previous classes. We considered, like single state multi-armed bandit problem, multiple states like multiple state reinforcement learning environment. When we come here, we simply consider model free reinforcement learning environment. So here we see algorithms that could be used when there is no abstraction of the environment, or when the agent does not know about the environment beforehand. So that is the idea. This is, more realistic than the previous sessions, because in the real world, we usually face problems to which we do not have that much information. So this type of reinforcement learning, like model-free reinforcement learning, is a type of problem we really need to address in a strategic way. So chapters from your textbook, like chapter 5 and 6 especially, should be consumed well. You should understand everything in those two chapters, but additionally you can also read chapter 7, chapter 9, and chapter 12. Just a quick recap. We said reinforcement learning is learning by interaction kind of thing, right? So we do have an agent. The agent imposes action on the environment. The environment will respond with the consequence, or we call it reward, and the immediate observation. It can also be, subsumed under the main theme or the main concept of consequence. So whenever some agent acts on the environment, then for that specific action, the environment provides some reward, and the state of the environment will be changed in a tantamount way to the action imposed on it before. So this is the whole cycle of reinforcement learning, or an agent that learns by interacting with the environment. So we said agents learn a policy, value function, or even a model, right? So for any action, there is a consequence, and the consequence of the same action could be different given different time steps. That's one important concept. And also when we extend the concept of consequences, we said decisions affect the reward, the agent state, and the environment state. This is what we already said here. In the last lecture, as you remember, or I tried to brief you a bit now, we discussed about model-based reinforcement learning. We discussed about MDP, with noun MDP actually. And then we tried to see, what value attrition means, or what Bellman expectation equation is, what Bellman optimality equation is. And in that way, we discussed a very, controlled feature of reinforcement learning, because we said there is a model, like a noun model of the environment, which is a noun MDP. From this chapter on, we'll be discussing about problems to which the agent does not have much information, and we can call them simply model-free reinforcement learning in general. The nature of the problem could be referred to as model-free. So from this chapter to onwards, we'll discuss about model-free prediction. Today's chapter is about model-free prediction. Given a noun MDP, that is the most important part. And then after prediction, because last time we have been discussing about this, right? We have a phase for prediction and a phase for control, the two important problems of reinforcement learning. So given this model-free RL environment in general, today we'll see how prediction could be made, specifically by using one algorithm, which is well known in model-free environment. And then in the next consecutive class, we'll see the extensions of these algorithms for model-free prediction, and also we'll extend our previous chapters for model-free control. Like in the previous chapter, we have seen different algorithms, including epsilon greedy, greedy UCB and alike algorithms. So we'll extend that concept to control in model-free reinforcement learning environment. And even today, we'll discuss a bit about function approximation, because in a model-free environment, we have to approximate some aspects of the environment, or we have to sample it, and based on that sample, we have to approximate upcoming results. So in the consecutive chapters, we will be discussing about this, like model-free prediction and control, function approximation. I will not be covering function approximation separately, but some concepts will be discussed in our today's session. And then most importantly, we'll discuss deep reinforcement learning, okay, and off-policy learning. So one of the prominent algorithms when we try to address reinforcement learning problems in model-free environments, especially for prediction purpose, is called Monte Carlo algorithm. We can mention more algorithms in this aspect, but Monte Carlo algorithm is a very old, well developed kind of algorithm, and it's really suitable type of algorithm to start with learning about model-free prediction, because this algorithm is kind of easy, and at the same time it has a lot of baggage. So for that purpose, it will give you insight. It will give you insight into the problems or the challenges of model-free prediction. So today, basically, we'll talk about model-free prediction, and we use Monte Carlo algorithm to solve our prediction problem. Okay, so let me give you a high-level overview of Monte Carlo algorithm, and then I will dive into the formalization of it. So when we say, for instance, in the previous class, dynamic programming or value iteration, or you call it policy iteration, there we have a noun MDP. So it's kind of a lookup table based problem solving, because for every state we will have value of state, and for every state and action pair we would have action value, right? So the MDP environment is there to provide us with this kind of information. So in that environment, we could use value iteration. That means value of state could be calculated. We could use the Bellman expectation equation, or we can also try to come up with policy iteration techniques that will give us the optimal policy among all possible policies. So that is kind of easier type of reinforcement learning problem with models at hand, models of the environment at hand. But usually, even at that class, we said this is not a realistic environment, right? So you may not have a complete model, like you may not have a full observation of the environment. So we discussed about partially observable Markov decision process. So in such kind of situations, we may have to start with some samples and execute simulations. Okay, simulations based on what you know, prior to the simulation, right? There's the execution of your solution. So when we talk about this sample-based simulated execution of solutions, one of the most prominent algorithms to simulate solutions based on some known samples of the environment is called Monte Carlo algorithm. So Monte Carlo algorithm is episodic reinforcement learning algorithm for prediction purpose. Am I not? Yeah, I'm recording, Sami. I'm recording it, but I haven't sent a single one. But the sound was kind of gibberish. I don't know why. Tasfa. Okay, nice. Tasfa is recording, so that's good. But we do have recordings for MDP. We do have recordings for the first chapter. So that's good news. And also I'm recording this chapter, so this session. So I think it's good. So I think Mabratu was also recording last time. Tasfa is recording today. So this is good. So, you know the concept of fault tolerance. So from any of the three, we'll get one good quality video. Okay, let me get back. So I was talking about Monte Carlo algorithm. So I said I was trying to give you a high level description of what Monte Carlo algorithm, and I was trying to set contexts, right? So in the previous class, it was model-based dynamic programming algorithms. So dynamic programming algorithms had their own problem. We'll discuss about this one when we talk about, I guess, function approximation later. But one of the most, significant problem, I would say, of dynamic programming is it requires model, and it's not realistic usually to have a model of the environment. So it's also slow, because it's kind of dictionary-based problem-solving technique. So if you have a larger MDP, a larger environment, a larger problem, then you will have a very slower reinforcement learning algorithm to solve your exploration and exploitation problems or prediction and control problems. So to avoid such kind of slower execution time or solution time, we came up with a new idea called sample-based reinforcement learning. That means this is basically model-free reinforcement learning. The agent will have preliminary interaction with the environment, and with that preliminary interaction with the environment, or even with special feature vectors, it may have some samples of the environment in general. Actually, I should paraphrase it as follows: like in this model-free environment, the agent initially will not have any interaction with the environment, but it will have access to a limited number of interactions with the environment. Okay, that's one thing. So when we come to Monte Carlo algorithm uses its experience, the agent uses its experience, we call those experiences samples, and tries to execute predictions, or we can also say explorations, for a specific number of steps or times. And for that specific purpose, we call Monte Carlo algorithm is episodic reinforcement learning algorithm for model-free prediction. So for instance, a Monte Carlo algorithm may have an episode of 1, for instance. So in this case, this Monte Carlo algorithm can be considered as a reinforcement learning algorithm in multi-armed bandit problem, because we said in that multi-armed bandit problem we considered only one state, right? But in case of Monte Carlo algorithm, you usually take more than one step. So an episode may have more than one consecutive step. So for an agent to declare end of life or end of lifespan, it may have to achieve, it has to achieve like a specific number of steps, which is declared as the episode of the agent. Okay, so for every episode of the agent, then this agent will try to simulate the same way we did before, but in the previous classes we have been referring to the MDP, or the kind of table or kind of dictionary, to know the value of state and the action value. But here we simply interact with the environment in simulated environment, because we do have parameters that represent the characteristics of the environment as a weight, like as a parameter, the same way you do for deep learning, neural networks, or for any machine learning, like gradient-based machine learning. Then for every episode, the model, in the case of evaluation, the agent will pick the best action state pair. Okay, the best action state pair, and from all those action state pairs with the best action value, it will construct the optimal solution up to that lifespan, that declared lifespan of the agent. So in generally speaking, I will go through the formalization of these concepts, but generally speaking, Monte Carlo is episodic algorithm, it's sample-based algorithm, it's model-free algorithm. That means it has no knowledge of the MDP. It only uses samples, and these samples can be referred to as experiences of the agent from its, initial, it could be initial assumption, or it could be some kind of empirical abstraction of the model, okay, the environment management. So let me start formalization of this Monte Carlo problem. If you understand how Monte Carlo problem algorithm solves our problem. So to take a simple example, for instance, if you take Monte Carlo, under this very known multi-armed bandit umbrella, for instance, for each action, average reward samples could be considered as a Monte Carlo. That means for like during the prediction phase, because we are learning about the prediction, during the prediction phase, an agent might try, like, say, 3 episodes, different policies, and somewhere in each of those 3 episodes, this action might be used, and somewhere else it might not be used. So what this algorithm does is, for each episode, if this action is taken, then the corresponding reward will be counted, and from the denominator side, the frequency of the action usage is also considered here. So across all episodes, this action usage given some state S is counted, and the expected, like the reward in a simulated environment we acquire from all those episodes will be taken here. But the catch here is that the best, during the policy evaluation, we'll talk about that. The best reward giver episode is the one who contributes this reward. Okay, this reward. For instance, the next from one episode, which contributes the better reward value for the same action. So simply, you can consider Monte Carlo algorithm, or the action value calculated by the Monte Carlo algorithm, as the average of rewards, the average reward samples, basically. Okay, so this basically means from our previous class we can compute this one as, or formulate this one as expected reward for the next step, because we are assuming the current action A at T. Okay, this means action value. Equivalently and incrementally, we can represent this one as this one, because last time, you remember, we discussed about how to incrementally represent action value equation. So here, for the next state, basically, is calculated as the sum of the estimated action value, this is it, plus factor, and the difference between time t. For the it's like the action is the current action, but its value in the next difference between the immediate reward of the immediate reward RT plus 1 and the action value, which is the previous reward given action AT. So since we are here considering a multi-armed bandit problem, that means we are considering a step of Monte Carlo, or episode size of Monte Carlo, as 1. So for that specific purpose, for all action which is not equal, basically consumed by, or traversed, or used, or executed by the Monte Carlo algorithm. Okay, that being said, now let's consider bandits with different problem. Here, we considered bandits with like the episode size of 1. Here, what we are considering is, let's consider bandits with different states. Different states means, like you consider multiple states at a time. So here, for instance, if you still consider, for instance, episodes as 1, we can say actions do not affect state transitions. That means there is no long-term consequences. Then if you want to estimate the action value, that means the value of state action pair, then we can pull the concept we know from the previous classes. So this action value can be calculated as the expected reward given the state of the agent and the current action. So if you take this one, for instance, the reinforcement learning problem, like updates its status based on its, based on the context of the samples it acquired by interacting with the environment consecutively, and this fact is called basically contextual bandit or contextual bandits, we can call this one. The process of some agent updating itself as it exposes or as it interacts with the environment. We call this process context bandit, basically. So this is a bit off topic, but we need this concept in this chapter. So I will discuss about function approximation a bit, and I will get back to Monte Carlo concepts, okay? Because we just discussed Monte Carlo from the perspective of model-based reinforcement learning, right? So we are trying to correlate Monte Carlo with, single-state, one-step, episode-based reinforcement learning problem in general, or the algorithm itself as that kind of algorithm. But since we are going to deal with model-free environment using Monte Carlo algorithm, and since we need samples to deal with model-free environment, the only way to get or to acquire those samples in model-free environment is called function approximation. Okay, so we have to know something about function approximation before discussing about Monte Carlo algorithm, which highly bases its essence on function approximation. So let's talk about function approximation now. The reason behind function approximation, or the need behind function approximation, is that in the previous class we have been, working with dictionary-based, as I already said, dictionary-based search spaces in general. So that means every state S has an entry value of state, or every state and action pair has an entry action value, or Q function value, Q of SA. But if you consider, large MDPs, as we already discussed, it might mean a larger dictionary or a larger lookup table in general. So this is not realistic because, we already said this one. We are going to run out of memory, and computationally it's also slow. So the other thing is that in most reinforcement learning problems or environments, individual states are not fully observable, right? The partial observability problem we have discussed before. So for that purpose, we need a function, okay? We need a function that can generalize based on its exposure as it exposes to the environment, and then build some kind of parameters, or we can call them feature vectors. Then this feature vector will be used to adapt to the new environment. You understand? So this is the basic essence of machine learning, I would say, adapting to the new environment. What we should do in order to make a model that adapts to the new environment, then we need to have a list of a vector of parameters that are fine-tuned for different exposures of the agent. That's the idea, whether it is active learning as reinforcement learning, or passive learning as any type of machine learning, any other type of machine learning. So for large Markov decision process, for large non-Markov decision process, I would say, we estimate the value function with function approximation techniques. Okay, so the value of state over this parameter W, you can also call them weights, by the way. So the value of state for every state, the value of state over parameter W could be considered as, or is equivalent to, in general, value of state over pi. So we know value of state over pi is calculated as W matter the optimal value of state in general. Okay, because this can be extended to this one. The same is true for the action value. The action value for a pair of S and A, some state and action, over some parameters W, is equivalent to the action value over a policy pi, or the maximum or the optimal action value. So what does it mean? The pi, the policy that yielded the optimal solution in the case of model-based algorithm. So this is basically a way to come up with optimal solution without having heuristic of the environment. Okay, even you can correlate it with previous class. So we call this W the parameter, and we can update this parameter because this is, reinforcement learning is kind of iterative process, right? So the update for this parameter W should be updated iteratively to resemble this policy, right? So for that purpose, the update on this parameter can be done by algorithms, model-free algorithms, like Monte Carlo and temporal difference learning. Today we'll talk about, we are already near parameter updates. For that, we will discuss about neural networks and then later about deep neural networks and other algorithms. Okay, so the idea here, because this is the most important slide of this session, the idea here is that we use function approximation to come up with this parameter W that resembles this policy pi in the case of model-based algorithms. Okay, and this can be extended to the situation where we are searching for the optimal value of state and the optimal action value. So how do we do this? We come up with this W that provides us with the best, or I would say, the policy that provides us with the policy that consecutively can yield to the optimal action value, optimal value of state by using algorithms like MC, TD, neural networks, deep neural networks, and other relevant algorithms for iterative update of parameters. So the idea here basically is that we tend to build interactions we will have as an agent, as an array agent with the environment is going to be the very first interaction. So that state, every state you encounter is unseen state. So your model, once you adjust it with the samples, okay, then your model will be able to generalize to those unseen states, and you will have a very good reinforcement learning solution, or the agent will be able to come up with an optimal solution in that environment. So how do we update the agent state? That is the other question. Here we discussed about the general algorithms we can use to update the parameters, right? So how do we update the agent state? Since in model-free environment, the environment is not fully observable, the agent state is updated by using the same update function we discussed in the previous class, but over a parameter W. This is the idea, okay? ST, this is the agent state, you know this. So for all these consecutive states of resembles the right agent state, okay? The right agent state. So basically, the parameter, as it is for other types of machine learning algorithms, like for deep learning, is an element of some kind of real numbers, okay? So the value of those real numbers, or the weights value will be altered depending on the suitability of that specific cell in that real number or in that vector with respect to the feature vector of the agent, basically. The feature vector of the agent at different time zones. We'll talk about that one later. So basically, ST denotes the agent state, okay? So this ST basically, you can consider it as a vector inside the agent, okay? A vector inside the agent. So for simplicity, you can also say, this is not usual, but you can also say ST is equal to OT. That means the agent state is equal to the current observation. That means the MDP environment is fully observable. We are still, inclining to the fully observability of the environment, but this is for ease of academics, So in this case, we can also consider ST, the agent state, as an observation. That's the fact. Now let's talk about linear function approximation. Here we'll talk about linear and nonlinear function approximation, because here we talked about two algorithms, right? MCTD as a linear function approximation techniques, nonlinear technique as neural networks are discussed here. Neural networks are gradient based, so we'll talk about that one later. So let's talk about linear function approximation, which are mainly based on feature vectors that corresponds to the different natures of the state over time. Okay, so we represent state because here we said st, the agent state can be taught or can be considered as a vector inside the agent. Basically, st could be considered like that. So let's represent the state by a feature vector. Let's say the function x of s is equal to the state of the nature of this state s at different time steps. You can say that like 1 is t is equal to 1, m is t is equal to m. So this we call it feature vector generally. So approximation techniques that mainly based on feature vectors, and we can consider feature vector as as a result of a function x which gives us the different value of states of the different estimates of that state s on different time steps. Okay, so here x as a function performs a mapping between some state to those real numbers are n, So you can consider this one as, for instance, if you consider distance of robot from different landmarks, then we can list the distance of steps or time interval. So this is a very linear representation of the agent state in the case of reinforcement learning over different time steps or over different incidents, I would say. Okay, so very important concepts. We are talking about linear function approximation. The most prominent component of this linear function approximation is feature vector. Feature vector holds the agent state value or state estimate, the value state estimate of the agent over different time steps. Okay, so the function that provides us this one is referred to as x. Now, in the next few slides, we'll be talking about the correlation or synergy between this weight and this. In the case of linear value function approximation, but we simply take the linear combination of those features we have discussed so far. What are those linear combinations of features? The first feature we have been discussing about was the parameter, right? The parameter, we will have the parameter, and then we will have the feature of that, the feature vector of that state. So this, for multiplication purpose, we transpose the weight or the parameter and multiply it with the feature vector of that same state episode, okay? Because the iteration is dependent on the size of the episode. So j starting from 1 to n means some number greater than 1 and defines the size. This iterative process, we do need objective functions. Usually the objective function in this case is a loss function. A loss function uses a square difference, so it's quadratic in w. So loss function given some parameter w is calculated as the expected squared difference between the value of state over pi and the estimated value of state over parameter w. So as you can see here, this is estimated value of state over w, okay? Value of state over pi of the algorithm given some fact, this is a fact, and the estimate over the parameter w. So the square difference, the reason for squaring, and this is to remove negative values. That's a basic example. So if you see here, in case of, for instance, we'll go back to Monte Carlo later, but let me take the example of Monte Carlo. In case of Monte Carlo, we usually traverse to n number of steps before calculating or before in general. So now let's talk about the update rule. How do we update? Okay, how do we update the values? So in order to update the value of some agent state, over a policy W, we can consider this fact, this basic fact. So the gradient of parameters, now this x of st from the from this one, okay, x of st. So in linear value approximation techniques, actually in non-linear, feature vector later. So the update basically is the product of step size, because here we have this step size or discount factor for that matter, you can say, prediction error, episode. So a special case of linear value approximation is table lookup features. In case of table lookup features, we usually use one hot feature to encode the feature vector basically. So this is basically, whenever, okay. So in this case, the weight W in this table lookup features, W contains value estimates for each state as the product of the one hot feature, the feature vector called one hot feature, which is combination of 0 and 1s, and the transpose of the parameter. So this can be rewritten as, the same way we wrote for the feature vector based linear function approximation. So for each of the weight or the parameters, then we will multiply it with the feature vector values, the corresponding feature vector, the state ማለት ነው. So let's get back to model free prediction. By the way, okay, let me get back to you before resuming the concept related. You can ask. አንዳንዴ እየሰማችሁኝም እንደሆነ ማረጋገጫ ነው። Okay. Samuel, do you know why we are discussing function approximation? ፊቸርስ የሚሆኑት ምን ይሆናሉ ማለት ነው? ፓራሜትርስ አይደለ? ፓራሜትሮቹን ለተለያዩ ኢንሲደንቶች ላይ ለሚገጥመን ሪዛልት ፋይን ቲዩን እያደረግን ሚሽን ለርኒንግ ላይ በምንሰራው ዌይቶቹን እያስተካከልን እንሄድና የተስተካከለ ኢንሲደንቶች አፕላይ ይደረጋል። አዳፕቴብል ነው ማለት ነው እንላለን። ኤጀንቱ አዳፕቴብል ነው ብለን እንወስዳለን። ያ ነው አይዲያው። ለምሳሌ ሞንቴ ካርሎ በእያንዳንዱ ኤፒሶድ የሆነ አክሽን እና ስቴት ፔር ይኖራል። ቤስት አክሽን ቫልዩ ያለውን አክሽን እና ስቴት ፔር የመምረጥ ጉዳይ ይሆናል ማለት ነው ፖሊሲ ኢቫሉዌሽኑ ጋር ሲመጣ። ስለዚህ እነዚህን መርጦ ነው የተሻለ ይረዳናል። እና ዶንት ሄሲቴት ኦኬ ኦልዌይስ። ኢንትረስቲንግ ጥያቄ አስቤው አላውቅም፣ ግን ጥሩ ጥያቄ ነው። ሶ ትራንስፈር ለርኒንግ ኔቸሩን እንየው። ዌይት በጣም ወደ ትራንስፈር ለርኒንጉ ሳይሆን ትራንስፈር ለርኒንግ የሚሆን ነው ብለህ ታስባለህ። ሶ ለዚህ ለተፈጠረበት ኢሹ ይጠቅማል ማለት ነው። that same weight could be taken for reinforcement learning ጎን ለጎን አድርገን ትራንስፈር ለርኒንግ የሚለውን ሀሳብ ብናነሳ ሜሽን ዌይት ይሰራል። ዌይቱን ኢንተርናሊ ኤጀንቱ ያለበትን አሁን ፌሲንግ ራይት ነው ኢትስ ፖሲብል። አግኝተኸኛል ሳሚ? ነገር ግን the very essence of ሞንቴ ካርሎን በለው ሊኒየር ፋንክሽን አፕሮክሲሜሽንን በለው ነን ሊኒየር ፋንክሽን አፕሮክሲሜሽንን ስታየው the very essence ከማጋ ነገር ሊተር ፋንክሽን አሁን ትራንስፈር ለርኒንግ ላይ ስትሄድ you do have decorator functions አይደለ? ምን ማለት ነው? ሞዴሉ ይኖርሃል። ለምሳሌ VGG ነው እንደው ለምሳሌ VGG 16 ከዚህ በፊት ስላወራን ኮምፒውተር ቪዥን ላይ VGG 16ን የተወሰነ ብሎክ ኦፍ ኮንቮሉሽናል ሌየሮቹ ተወስድና ኦን ቶፕ ኦፍ ኢት የሆነ ነገር አድርገህበት ፌስ ሪኮግኒሽን ላርገው ልትል ትችላለህ። ኦብጀክት ትራኪንግ ላርገው ኦብጀክት ሪኮግኒሽን ማለት ነው። እዚህ ጋር ግን ስትመጣ there is no decorator function, you do have weight, you simply apply those weights to solve the consecutive or subsequent problems you have ማለት ነው እና usually in okay okay በጣም በጣም okay let me proceed almost እየጨረስኩኝ ነው I'm sorry ጊዜያችሁን ወስጃለሁ okay Monte Carlo algorithm and model free prediction ነው እያየን ያለ ነው right Monte Carlo algorithm so let's talk about bandits with state so we have been discussing about this while talking about function approximation linear function approximation but consider it as a revision and also consider it as something new in relation to Monte Carlo የምናወራበት ሴሽን ነው ብላችሁ አስቡ ማለት ነው so here the objective function loss ብለን የሰራ ነው አለ አይደለም so this loss function basically ምንድነው the expected square difference now to talk about the gradient update we are not going to talk about only the feature vectors but we are going to ascend a bit to gradient based model free reinforcement learning basically so how do we update the weight at time t plus 1 being at time t basically ቅድም የሰራንበት መንገድ so the weight this weight this is vector basically is updated by the loss or the objective function loss result of the weights or the parameters w at time t expected error and then the expected error basically the expected error times what we said before step size prediction error and basically referred to as stochastic gradient update this whole process so I think the gradient update or the gradient descent is already known basically we tend to minimize the loss function as you go here stochastic gradient update is a type of gradient update or for the gradient descent in which you only take some samples of the loss function not all samples so that's why we are saying stochastic gradient update basically stochastic gradient update is a gradient update for a subset of the objective functions or for the subset of the agent's possibility agent state's possibility so difference if you know gradient update how gradient update is done for deep learning then stochastic gradient update here in the Monte Carlo side is basically done for a sampled loss functions and then for a sampled exposures of the agent ማለት ነው okay so when you use linear functions the action value for a pair of state and action is calculated as we did in the previous linear function approximation slides it's a product of the transpose of the parameters and the gradient xsa in the case of this okay xsa is the gradient so we can replace this one vector or you can say the gradient and a at time t over the parameter w at time t at that specific time so this stochastic gradient update is calculated as this action value over a parameter w and this gradient xsa here in the previous class we were talking about what to read about the difference between feature vector and gradient we have already discussed this one but the difference between feature vector and gradient so we discussed x of s is a feature vector x of sa is a gradient okay so now once we have this the next step would be policy evaluation okay so for this we consider sequential decision problems and the goal of this policy evaluation is to learn the value of state over pi from episodes of experience under policy pi mind you So when I start this session, I say a given agent might check through multiple episodes, okay, for any policy pi. So the policy evaluation, the purpose of the policy evaluation is to learn a good policy, okay, from all those episodes that provides the maximum action value for a pair of S and A, okay, at any of those three episodes. So basically, to come up with maximum return in order for it to be selected as the target pi value according to Monte Carlo. Okay, so this is like inter-episode evaluation of action values. In the previous class, we have been considering, per policy action value. Now we are considering that the agent might have more than one episodes, and in each of those episodes, it might expose itself to various rewards pertinent to the actions it took and the time that action is taken. Then the evaluation phase of this Monte Carlo is responsible to select a policy that provided the maximum action values in most of the cases, okay? So if you have like three policies, the policy with the better action value across those three episodes is chosen as the one, okay? So that being said, the return, according to Monte Carlo, okay, the return is the total discounted reward. This is the same as what we have done before in the model-based algorithm. The return is the same. The only difference is the limit. Here we say t minus 1, small t minus 1, is traversal of the agent, but for specific episode size. Okay, so basically, let me correlate this one with another kind of unrelated, but in some way it is related. For instance, if you see, when you call the concept of Deb's first search, we introduced ourselves with iterative deepening technique, right? In iterative deepening technique, we usually do what? We limit the depths of the search tree, and then for the first time, for instance, if we start with a search tree depth of 3, so for 3 levels we will traverse and try to find the solution, right? So in this sense, Monte Carlo is the same because it has this limiter or threshold called episode, and this episode has a finite number of steps. For instance, if this finite number of steps is the same as the maximum possible traversal of the agent on that environment, then there is no special benefit we can get by using Monte Carlo algorithm. Okay, but if you take like 100 possible traversals, and from those 100 possible traversals, if you decide to simulate based on 3 exposures for the remaining 97 possible traversals or problem spaces, then Monte Carlo is beneficial. Okay, the difference between Monte Carlo in this specific sense and iterative deepening is that whenever you couldn't find solutions in the case of the first depths, like you usually increase the depths like size, right? 2, 3 up to the end of the search tree. In this case, you usually use different episodes with different policy, but the same size of the episodes, which is shared among all those other episodes. So this is the idea. So once you get this, when we begin this class, we talked about the presentation of Monte Carlo. So in this same sense, for all episodes, if you get action value for a pair of S and A, then you use those frequencies as a denominator, and you use those value estimates as a numerator, and then sum those estimates at the numerator place and average them. Okay, so those sample average could be used as expected return value for that specific action state pair. So this process in general is called Monte Carlo policy evaluation. So now let's talk about the disadvantages of Monte Carlo, so that it gives you this gives you like another perspective of Monte Carlo. If you are not really clear about what Monte Carlo is, these limitations will give you a clear perspective. The first one, uh, Monte Carlo is episode based, so this is kind of good. Okay, this is kind of good because it will enable you to like I'm considering you as an agent. It will enable you to learn quickly. That's good. But what if you have to have like larger size exposures? What if you have to have longer episodes? Okay, in order to come up with optimal solutions. So in that case, the learning process can still be slow, and also the same problem we have been facing during the model-based reinforcement learning could be here, like could appear here, because the longer episode, the longer traversal the agent would make. That means you need to have like memory, so the algorithm will be memory intensive, resource intensive. So this is mainly due to the fact that Monte Carlo algorithm, Monte Carlo algorithm calculates the value estimate after traversing all those steps limited for a single episode. For instance, if an episode has to traverse 10 steps, then the agent will go to all those 10 steps and try to come up with a state action pair which is better than all other action pairs in that episode. So for this specific purpose, it's going to be slow, right? And so it's going to be memory intensive for larger reinforcement learning problems. So do we have alternatives, for instance, in this case? Yes, we do have alternatives. Rather than checking the value of estimates or like the returns of an agent after the end of an episode, we can do it after some time interval or after some time step, like after a fixed time step. For instance, if the episode is like say 10 step time step, then you can simply check at every 2 time steps for the better solution. So that way you will be able to identify state action pairs which performs well, and this makes this time step based model free reinforcement learning algorithm a better alternative. And the name of this algorithm is called TD learning algorithm, or temporal difference learning algorithm. So temporal difference learning algorithm is almost the same as Monte Carlo algorithm, but it's the time it performs policy evaluation is more fine-grained than Monte Carlo algorithm. So in a way, it's faster, and also it doesn't have that much big memory requirement compared to